Hello everybody. In today's video, we're going to go step by step through some examples and we're going to find the pH and hydroxide concentrations for salt solutions formed with weak acids and weak bases, including the conjugate salts. Alright, in this question we're told that the Ka for hydrofluoric acid is 6.8 times 10 to the negative 4. And what we need to do is find the concentration of hydroxide and the pH of a 0.12 molar sodium fluoride solution. So the first thing that we have to do is to understand that sodium fluoride, when it's mixed into water, that this is going to fully dissociate into a sodium ion and also a fluorine ion. And we know by now that the sodium is going to be neutral, meaning it's not going to affect the pH. So we can basically ignore that and just focus on our fluorine ion, so that when we write the equation, we don't have to add the sodium. We can just write the fluorine plus our water, and when we do that, it's going to give us hydrofluoric acid, and it's also giving us hydroxide. And we know that hydroxide is going to increase the pH, which means that it's a base. And since we're dealing with a base, we can't use the Ka, because Ka is for acids. So we know that the relationship between Kb and Ka is that when you multiply them, that will give you Kw. So if we want to get Kb by itself, we just switch it around and put Kw over Ka. Now what is Kw? Kw is a constant that's going to be given to us, the ion product constant of water. And Kw is always going to be 1 times 10 to the negative 14. Perfect. All we're missing is Ka. No, we're not. It's given to us. 6.8 times 10 to the negative 4. And this is good. This is what we need to find the Kb. So if we take 1 times 10 to the negative 14 and we divide it by 6.8 times 10 to the negative 4, that's going to give us our Kb. In this case, our Kb is going to be equal to 1.47 times 10 to the negative 11. Perfect. That's our Kb. Now that we have the Kb, we just have to write the formula for that Kb. And this, we're going to be using the ice chart. Now, what can we fill in right now that we already have? Well, it tells us that we have 0.12 molar of sodium fluoride. I told you that we don't have to worry about the sodium. So we know that since it's a 1-to-1 ratio when dissociated, that we can write for the fluorine concentration 0.12, the initial concentration. Water, since it's a liquid, we're going to ignore this. This doesn't count for anything. And we don't have any products yet, so we write 0 and 0. And for the change, we're just going to denote it as x for now, since we don't know what that is. And since things will be moving from the reactants to the products, we'll do minus x. And here we're going to be gaining x plus x plus x. Now at equilibrium, it's just going to be 0.1 minus x. So we'll still just write that. We don't know what that is yet. If we start with 0, we add x, we'll get x. Same here for the hydroxide. Now that we have this, we have to write our Kb formula. And we know that Kb is always going to be the concentration of the products over the concentration of the reactants. Now, all we have to do is fill in at equilibrium. Fill in the concentrations that we have for each of our reactants and products. Alright, now I erased part of the ice chart because all we're really interested is what those values will be at equilibrium. So our Kb formula is going to be 1.47 times 10 to the negative 11, which we figured out from taking the Kw divided by Ka, which is formed in the question. And it's going to be equal to those product concentrations, in this case x and x. When we multiply them, we'll just get x squared divided by the concentration at equilibrium of our reactants. In this case, 0.12 minus x. So if I erase this to make more room, what we're going to want to do is to get x by itself. Or what we're going to want to do, is to write it in the quadratic formula form. So when we're done moving things around, this is where we're going to want to be. Set everything equal to 0. So the first thing that we can do, this is equal to x squared divided by 0.12 minus x, is just multiply both sides by this amount to get rid of the denominator. So if we take 1.47 times 10 to the negative 11 times, still in parentheses, 0.12 minus x is going to be equal to x squared. Now, erase this, since we're going to slowly be changing this formula, manipulating it. Now, all we have to do is distribute this kb into each of those values in parentheses. So if we take 1.47 times 10 to the negative 11, we multiply it first by 0.12, we'll get this number. Do that, we'll get 1.76 times 10 to the negative 12. And now we multiply it again, this time by negative x. So we'll write minus, and it's just simply the same, 1.47 times 10 to the negative 11 x. This is not multiplying, this is x. Is equal to x squared. Almost there. Now, once we rearrange it a little bit more to get it equal to 0, we'll get x squared plus, so we have to add this to both sides, plus 1.47 times 10 to the negative 11x minus, subtract this amount from both sides, minus 1.76 times 10 to the negative 12. Now everything is equal to 0. Perfect. That's exactly what we want. Now, when we plug this into the quadratic formula, our A is just going to be 1. There's nothing in front of it. This will be our B minus our C. We have to remember to put negative C. Perfect. Now putting that into the formula, A is 1, B is going to be 1.47 times 10 to the negative 11, and our C is going to be negative 1.76. Negative 1.76 times 10 to the negative 12 power. Perfect. So, I'll erase this. And when we put that into the formula, it's going to give us two answers. It's going to give us 2. The first one is negative 1.327 times 10 to the negative 6. And the second one is 1.3266 times 10 to the negative 6. Now, which one do we use? If we know previously, x cannot be negative, because at equilibrium, this is going to be an x, and this will also be an x. And this, remember, is 0.12 minus x. Now this can't be negative because we don't have anything to begin with, so there's nothing to take away. So we're always going to pick the positive x. So this is the one that we want. This one. So if we're looking for the concentration of hydroxide, and we know that our x is this amount, we're going to find that that's going to be our concentration at equilibrium. So our concentration of hydroxide is going to be equal to, let me make more room here, 1.327, I'll round it, times 10 to the negative 6. Perfect. That's one part of the question. We're still looking for is the pH. So how do we get to pH if we have the concentration of hydroxide? Well, the first thing that we can do is find the pOH. And the pOH, remember, the P meaning negative log. So we'll take the negative log of our hydroxide concentration, which is 1.327 times 10 to the negative 6. This will give us our pOH, sorry. pOH, when we do that with the calculator, negative log of 1.327 times 10 to the negative 6 is going to give us a pOH 5.877. Now, we still need to get the pH. So in order to get to the pH, remember that formula, that pH plus pOH is going to always equal 14. When we rewrite that, in order to find the pH, we can do 14 minus whatever that pOH is, in this case 5.877. That's going to give us our pH. So we'll do that, and that's going to give us a value for our pH of 8.123. And there we have our pH, and also we were looking for the concentration of hydroxide, which we can write out. Concentration of hydroxide ions is equal to 1.327 times 10 to the negative 6. Those are our two answers. Alright, in this next question, we're told that the dissociation constants for carbonic acid are here written out. And we need to find the hydroxide concentration of a 0.1 molar sodium carbonate solution. So, first thing that we always do is we always look at how was this going to dissociate. It'll fully dissociate when it's mixed in water, giving us 2 sodiums and 1 carbonate. Now, remember what we said. Sodiums don't affect the pH, they're neutral. So we can just ignore this. So now we're going to write the equation for when we mix that carbonate into a solution with water. So we can write CO3, 2 minus, plus H2O, and this carbonate's just going to steal 1 hydrogen. You can only steal 1 at a time. That will give us HCO3 plus, let me make room here. If we took one of the hydrogens from that water, that means all that's left is OH. Perfect. That's our equation right now. And we'll draw out that ice chart that we're going to use. Ice right there. Now we see in the products that we're given a hydroxide. Well, hydroxide means that we're going to be utilizing Kb, since this is going to increase the pH, making it basic. So we remember the relationship between Ka and Kb. If we want to get Kb by itself, it's that Kw that ion constant for water, divided by the Ka. We know Kw is always going to be 1 times 10 to the negative 14th. However, here, Ka, we have 2. Which one do we use? Now, this is where it can get a little bit complicated. For this carbonic acid, you always have to remember that it can only donate 1 hydrogen at a time. So that's why we're giving 2 dissociation constants. So for the first one, that carbonic acid, H2CO3, it's going to give up 1 hydrogen, and then we'll be left with HCO3. So that's going to give us the Ka for the first one. Then the second one, we start with this, HCO3, because it still has 1 more to donate. And then that gives us H plus CO3. That's why we have 2 values for the Ka. Which one do we use? Well, it's really important which one we pick. So we have to look at this, HCO3. Remember that it takes 1, and that this is going to be the conjugate acid for a conjugate base. What that basically means is that this has a hydrogen ion and this doesn't. Whichever one has the hydrogen is going to be the acid. So that's why we're going to use Ka1 as our value, HCO3. That's going to be the Ka that we use. So now that we know we're using Ka1, we'll just write that into that equation. 4.3 times 10 to the negative 7. And then when we multiply those and then we divide them, we'll get the Kb. So let's do 1 times 10 to the negative 14th. Divide that by 4.3 times 10 to the negative 7. We'll get our Kb value. So Kb now will be 2.33 times 10 to the negative 8. That's our Kb. So now that we know our Kb, we have our ice chart set up, we're going to write out that Kb formula, which was the concentration at equilibrium of our products over the reactants. Let's clean this up. Here. Alright, so if we're told that a 0.1 molar sodium carbonate solution, and we know that the sodium goes away and it doesn't affect our pH, we know that that 0.1 is also going to be the concentration for Cl3. So we'll write 0.1, water, liquid, doesn't matter. Cross that out. We don't care about that. We don't have any products yet, so we'll write 0, 0. This will decrease by x, so then these will increase by x. And then equilibrium, if we start with 0.1 and we subtract x. Start with 0 and then we'll just add x. Perfect. Now we can write our Kb formula. If we know that Kb is 2.33 times 10 to the negative 8, that's going to be equal to, when we multiply the products, x squared, we divide it by our reactants, 0.1 minus x. Perfect. Now we're going to rearrange this formula to get that quadratic formula, ax squared plus bx plus c is equal to 0. Now that we've manipulated that formula into giving us our quadratic form, we know that our a is just going to be 1, this will be our b, and this will be our c, negative, since we're subtracting. Now once we put that into the formula, it's going to give us 2 x values. So one of our x values will be 4.83 times 10 to the negative 5th. Our other x value will be negative 4.83 times 10 to the negative fifth. And we know now that we never choose the negative one. So the first x value is what we want. So we know our x is going to be 4.83 times 10 to the negative fifth. What can we do with that? What are we looking for? We have to remember, we have to find the hydroxide concentration, which is easy. We know that that's just x. So we can write our hydroxide concentration is going to be equal to 4.83 times 10 to the negative fifth. That's perfect. That's the first step. Awesome. Now, that's all that it's asking us in this question, but let's test ourselves a little bit. Let's try to find the pH of this solution. So if we want pH and we have a concentration of hydroxide, first thing we can do with that is find the pOH. So our pOH will just be the negative log of that number, 4.83 times 10 to the negative fifth. Let's do that. Let's do negative log of 4.83 times 10 to the negative fifth. If we do that, it's going to give us a pOH of 4.316. All we have to do to find the pH is just take that number and subtract it from 14. And once we do that, we'll find that the pH is equal to 9.68. Beautiful. Now we were able to find hydroxide concentration and our pH. Thanks for watching. If you have any questions or if you found this useful, please let me know in the comments and I'll make sure to get back to you as soon as I can. Have a great day.